Hello everyone, this is Prahlad. My friends Karan and Mridul will join me in presenting a multi-agent reinforcement learning approach for stock portfolio allocation. We are recent graduates with a degree in computer science and engineering from NIT Warangal. Let's get started. We first go through a quick overview of our presentation. We start by providing a problem description and cover some background about deep reinforcement learning. Then we discuss our aim and motivation behind going for multi-agent reinforcement learning and provide the details of our experimental setup. Finally, we analyze the results obtained and conclude our presentation.
We now describe a problem statement. Stock portfolio allocation is the problem of finding an optimal investment strategy for a curated collection of stocks, such that the trader maximizes returns while minimizing the risk involved. It is considered as one of the most challenging and interesting problems in modern finance because of the difficult to predict nature of the stock market arising from its complex and evolving dynamics. The problem of portfolio allocation involves sequential decision making, which is mathematically expressed as a Markov decision process. Reinforcement learning has proven to be a powerful tool to solve such class of problems. It has been used to develop intelligent agents that could learn complex strategies as shown by many empirical works. It is noteworthy to observe that many of the widely accepted and practical applications of reinforcement learning are in domains that generally warrant only a single agent. That is, the task at hand could be solved sufficiently by having a single agent interacting with the environment and taking actions, obtaining rewards, and improving policy. But in real life scenarios, such as the one in consideration, there are hundreds of thousands of traders interacting with the stock market every second. The resulting complexity is therefore incredibly difficult to predict by a single agent learning model. This motivated us toward considering multi agent reinforcement learning for our problem. Specifically, we aim to explore the applicability of multi-agent reinforcement learning by implementing single-agent, two-agent, three-agent, and four-agent deep deterministic policy gradient variants and compare results across standardized matrix.
We now provide a brief overview of multi-agent reinforcement learning, abbreviated as MARL. MARL is an extension to the single agent reinforcement learning model whereby every agent has an influence on the environment. As the figure here illustrates, each agent receives an observation as the state, takes an action based on its policy, and receives an appropriate reward from the environment. Mathematically, this setup is modeled as a Markov game. In reinforcement learning, actor-critic methods have gained a lot of attention because they utilize the best of both the value-based and policy-based learning methods. Here, with its current policy, the actor decides which action to take based on the state, and the environment provides the reward for that action. The critic then updates the value function and tells the actor how good its action was so that the actor can then update the policy accordingly. Both the actor and the critic are function approximators, and in this case, are neural networks. With this background, let us now discuss the multi-agent deep deterministic policy gradients algorithm, abbreviated as MADDPG. This is the algorithm we use for our experiment. MADDPG is an actor-critic method that uses a framework of centralized training and decentralized execution, wherein multi-agent policies are allowed to use additional information obtained from all agents during training, while ensuring that only local information is used by agents during execution. As in real life, agents aren't usually fully aware of each other's actions and observations. This is done by providing the critic networks, shown here as the queues, with the observations and actions of all agents, but maintaining the policy networks, shown here as the pies, to observations and actions of the corresponding agent only. Now, why did we choose MADDPG? Because MADDPG is an actor-critic approach. It avoids the several issues faced by value-based methods and policy-based methods such as convergence and learning instability. It does not assume a differentiable model of the environment. It does not impose any particular structure on the communication method between agents. It can be used in cooperative, competitive, and mixed environments. It led to state-of-the-art results in learning multi-agent policies as shown in the figure. We now detail the setup of our experiments. We consider the Indian stock market of the Bombay Stock Exchange. For our stock portfolio, we choose 30 stocks that are traded in the BSE. These stocks are reputed and chosen across several industries and businesses to evaluate our model's robustness in handling varied stock portfolios. We provide an initial balance of 1 lakh rupees to the agents to facilitate trading. Let us now make our problem more mathematically concrete by defining it as a Markov game, the primary aspects of which are that an agent is treated as a trader and the environment is the Bombay Stock Exchange. N represents the number of agents. In our experiment, it ranges from 1 to 4. T is a time horizon, consists of every trading day from January 2008 to December 2019. AIT is a set of actions for the agent I on day T. Each agent can take 3 actions: buy, hold, or sell. An action is performed once a day. The agent can trade up to 5 stocks at once. SIT is a set of states for the agent I on day T. The state of each agent consists of three main parts: the closing prices of the 30 stocks, quantity of each of the stocks held by the agent, and the balance available with the agent on the day T. Portfolio value of the state SIT is the total asset value with the trader, which includes the total worth of stocks held and available balance. RIT is the return the agent I receives on day T. This is defined as the change in portfolio value before and after the agent I's trade on day T. There is no cooperation between the agents. Each agent pursues individual self-interest to attain maximum expected return, which is the discounted cumulative sum of rewards as shown. Intuitively, it can be seen from a problem definition that the data needed for our experiment will be the daily closing prices for the 30 stocks in consideration for every trading day in the full timeline from January 2008 to December 2019. We obtained this data from the Bombay Stock Exchange's official website, downloadable in the CSV format. Apart from the historical stock prices, there is no other external data fed into the model. We divide our dataset into training and testing data as shown. We note that inherently the data itself is neither cooperative nor competitive, but it is our reward structure that makes the environment non-cooperative. There is no further pre-processing done on the data. Some of the main constraints and assumptions with our experiment include the following. Each agent can only take one trading action in a day and can buy or sell up to 5 stocks at once only. This is done to limit extreme decisions by the agents. Agents do not communicate with each other directly in our experiment. Agents cannot reallocate or diversify their portfolios to other stocks or other assets such as in bank deposits or on real estate, etc. We assume the absence of multiple exogenous constraints on traders such as transaction costs, trading restrictions, cash holding restrictions, and so on. We implement the MADDPG algorithm with PyTorch and simulate the stock market environment using Python. The values of hyperparameters such as the discount factor and the learning rates are set as shown. The number of episodes we trained for the model did not exceed 100. As shown in the top right, the execution time on average grew rapidly with the introduction of multiple agents. We trained our models on the system specifications as shown in the bottom right.
We now proceed to detail the obtained performance results for each of our models on four main standardized metrics, namely Sharpe ratio provides a measure of unit of return per unit of risk. Annualized return signifies the quantity of yearly yields from the portfolio. Annualized standard deviation error represents the amount of risk taken by the model, which in investment terms is a measure of the price volatility. Final portfolio value. It is the eventual return on investment at the last day of trading. The resulting performance metrics obtained are as shown in the table. We know that as the number of agents is increased, the model improves performance. The 4-agent model is shown to have the best Sharpe ratio of nearly 1.5 and achieves the highest yearly return at roughly 25%. It also achieves the highest final portfolio value by nearly doubling its initial balance. However, the portfolio allocation that follows the Sensex index, which is a BSE market weighted index of 30 stocks, has the lowest annualized error at 0.119, followed by the 4-agent model. The same trend is confirmed by various metrics when we observe the portfolio values plot. The portfolio value is shown on the y-axis and the dates are shown on the x-axis. The 5 lines in the plot show the portfolio value growth over time for one agent using DDPG, for 2, 3 and 4 agents using MADDPG, and lastly the Sensex based portfolio. It can be observed from the plot that the 4-agent model achieves better growth of portfolio compared to all the other models and majorly outperforms the market index as well, indicating best returns. However, it's noteworthy to observe the increased portfolio value variance and volatility among the multi-agent models. We conclude our presentation with a few takeaways. We have shown the applicability of multi-agent reinforcement learning for stock portfolio allocation, a field that is currently underexplored but has a lot of potential. The overall empirical performance of our models improves significantly with the introduction of multiple agents. Our 4-agent MADDPG had the best trading strategy and outperformed the benchmark Sensex index. The Sensex based portfolio follows a more stable, lower risk but less profitable strategy as compared to the 4-agent model. Going forward, we are looking to improve model stability and attempt at better modeling the market by introducing groups of cooperative agents that compete against other such groups. We are also looking to provide richer data to our model by incorporating investor sentiment along with other company performance metrics to further improve performance.